Hello and welcome to this new series of tutorial on hashing. My goal actually is to teach one hashing algorithm. So I'll be talking about SHA-256, then one symmetrical encryption, AES, which we discussed in the last set of tutorial, and then I'll be treating an asymmetrical encryption, which we'll be talking about in the next series of tutorials. So in this tutorial, I'll be talking about SHA-256. So you can head over to projectfpga.com/SHA-256 to get a brief introduction to this tutorial. So when you go over to the site, you're going to see the introductory part of this tutorial, the definitions, the theory behind the hashing. I made it very brief and concise. So but my major lecture in this tutorial is about the logisim code block. I'm going to be talking about how to implement this in Verilog. So I'll be using some set of logisim circuits to explain how SHA-256 works in Verilog. So let me just go briefly over what it is. So we know SHA-256 is not an encryption, it's hashing. So you get, so here I've listed some functions of a cryptographic hash, including same message always results in the same hash, always, because it's more as an algorithm or a set of protocol. So no matter whether you're writing it in Java, you're writing it in Python, you are explaining it in Verilog or VHDL, the same hashing algorithm, you are still going to get the same result for the same hash. It's quick to compute. So that is one properties of a very good hashing algorithm. So you know, like we have SHA-256, we also have SHA-512. So the higher, the more complex, the more secure, but the less easy it is to compute, and the more computing power it takes. So SHA-256 is very good. Then again, is invisible to generate a message that uses a given hash. So that is one very important characteristics. You can't generate the same message using two different hash values, or you can't generate the same hash value from two different distinct messages, irrespective of what they look like, whether they're exactly the same and missing a full stop or a comma, they can't be the same again. So that's the same thing here and then here. So that's that about the brief introduction I've given here, the benefits of hashing. So remember, we treated encryption in the last tutorial, then I will still talk about asymmetrical encryption in the next tutorial after this. Then there here I listed types of hashing, MD5, SHA-2. So I've actually picked SHA-256 actually. When you go to the site, you see procedure, how it works. But for this set of video tutorial, I'll be talking about Verilog codes, how to write SHA-256 in Verilog. So as you can see, these are sets of codes which are my major point of concentration. So hopefully before you start going through this tutorial, please kindly try to get a brief idea, the theory behind SHA-256, because this video is all about the Verilog code, how to implement SHA-256 in Verilog. So we'll be using this set of examples I've given here. You can find it at projectfpga.com/SHA-256/code.php. I'll also keep a link in the description below. So I'm using projectfpga.com as an example. I'm trying to hash this using SHA-256 in Verilog. So the first step is obviously you have to convert anything you are dealing with in bits. You have to convert it to binary. So I had to convert project FPGA to binary, so I got this. You can check it online how you convert text to binary. You first convert to ASCII, then ASCII to binary. So when you do that, you get this. Then now what I'm trying to explain to you here is the algorithm behind SHA-256. So the step-by-step procedure. So whenever I want to hash, the first step is to first convert it to binary. Then next step, you add 1 to the end of the data. So if this is the binary conversion of projectfpga.com, then I have to append 1 to it. So that's the second step. Then again, remove this. Okay. Then step 3 says filling with zeros until the data become a multiple of 512. So that's the third step in this algorithm. So remember, our SHA-256 stopped somewhere around here. Sorry, this is not okay. So this is it. Plus we appended 1. This is the one. So it says add zeros to it until it becomes a multiple of 512. So whatever you get from the conversion, whether you are hashing projectfpga.com or some other long sentence, what it's saying is after the conversion and adding of 1 to it, pad it with zeros. It's more like padding. Pad it with zeros until it's up to 512. So that is a third step in this hashing algorithm. Then the next step is add 64 to the end, 64 bits to the end, where 64 bits is a big endian integer denoting the length of the input data in binary. In our case 120. In binary this is so what it's saying in essence is it says count this binary conversion, count it. How many is it? It's 120 when you count it, because let me check. This is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 by 8. It should be what? Let me so what is saying, okay, it's 15, so we do 15 by 8 is 120. So what it's saying is count it. How many bits is it? Is 120 bits. So that 120, convert it to binary, then you replace the last, after we appended up to 512, you replace this last one with that 120. When you convert 120 to binary, you get this. So you now took this and appended it here. I don't know if you understand this. So you count the number of bits, you don't include the padded bits actually, just the proper bits, and then append it. So this is when we appended 120 again to the end. Then again, now it says now we have an input that's always be divisible by 512 probably. Okay, let me just ignore this particular statement. Hope you understand that. Then it now says let's create. So now this is where my Verilog code actually starts. So from here upwards, I didn't actually include it in the Verilog code. From here upwards till step number 1, we're not included in the Verilog code. So from here, from step 2, so everything upwards is like the major step 1. I describe it as the pre-processing step. Pre-processing. So everything above here, I describe this as the pre-processing step. So here I officially starts. This is where the Verilog code officially starts. the step 2, initializing hashing values. So let's see. It says let's create 8 hash constants. We're going to make 8 hash constants. These are constants representing the first 32 bits of the fractional part of the square root of the 8 prime numbers. So these are the first 8 prime numbers here. So this is more like so these are the fractional parts. I don't know, these are the fractional parts they're talking about. So you can either see them as constants, or you can try to derive them by dividing these prime numbers and getting the fractional parts in hexadecimal. But these are what they represent. So they are more like constants in SHA-256. So I've implemented them in Verilog using this code. So please kindly follow these Verilog codes step by step, because they are more like sub-circuits. At the end, I'm going to fuse them all together to get a working SHA-256 block. So I have described it as SHA-256 H_0. So let me show you what this looks like in Logisim. SHA-H_0. So this is what it looks like here in Logisim. So these are those constants we just saw. These are all of them. So I'm actually storing them within these outputs, out 0 to out 7. They're actually 8 in number. So I'm actually more like storing them. So this sub-circuit is not actually all that necessary. So okay, I'm going to do something now. I think probably I have to pause this, but okay, but okay, I'm going to do something. So it won't be confusing. So these are the constants. I'm actually storing them in these outputs. So I'm going to be using them as a sub-circuit in our future tutorial. So follow me patiently. This is the first part of the Verilog code, trying to get these constants. So I've stored them within these blocks, out 0 to out 7. So let's continue following briefly. Then again, so this code here stores those constants. So that is the first Logisim code. Now the next step 3, initializing of round constant scale. So it says let's create some more constants. We've already created the first 8 constants, so this time 64 of them. Each value is the first 32 bits of the fractional part of the cube root of the 64 prime numbers. The first 8 constants we had earlier were square roots of the first 8 prime numbers. Now these are the fractional parts of the square roots of the 8 prime numbers. Now what we are having now is the fractional parts of the cube root of the first 64 prime numbers. So they are likewise constants also. So these are all of them. They are 64 in number. You can either, if you're a mathematician, you can either try to derive them, or you can actually see them as a constant. So this is the Verilog code where I created them. So all these codes are actually sub-circuits to a bigger circuit. So at the end, it is going to give us our SHA-256 system, our SHA-256 circuit. So I call this SHA-256 K machine. It's called the K machine. So K machine is more like a constant machine, the K machine. So let me check it. So this is it. Let me get the circuit. Yeah, it's much here. Okay. Oops, very no. I'm coming. Oh, So this is it. These are the constants actually. So hopefully you have an idea of logisim. So in logisim, you know very well that these symbols represent constants. Everything down here, they are all constants. So I'm actually feeding them. This is not a perfect drawing. Let me draw it properly. So these are all constants. So I'm actually feeding them into 63 outputs. So I'm actually feeding them into the 63 outputs. So this circuit you are seeing here, this is the verilog code for it. So hopefully if you don't understand it in logisim, you will understand it while going through the verilog code. So remember, we already have, it's just as saying, if you don't understand it in logisim, you understand it in verilog code. So already we have the first 8 constants, which are the fractional part of the square root of the first 8 prime numbers. Now these are the cube roots of the fractional part of the cube roots of the first 64 prime numbers. So these are constants which are used to hash, are used in hashing SHA-256. So you are going to see how these constants were used to obfuscate this SHA-256. Okay, now we go to step 4. So after this we come down to step 4. So the step 4 says copy the inputs from step 1 into a new array where each record is a 32-bit word. So what is saying, you know, earlier they were actually divided into 8. So this actually, before earlier they were into 8 bytes. They were into bytes by bytes. Sorry, this is what I mean. They were into bytes. Each of them were into bytes. So what step 4 is saying is that you should move them into 32 bits, no more bytes. So instead of bytes, you have now shared them back into 32 bits per block. Instead of a byte per block, they are now divided into 32 bits per block. So it now says add 48 more words, initialize to 0 to get an array of 0 to 63. So you know, when you spread it 32 instead of initial 8, they actually reduce. They are no longer 64. So it needs 48 more. So it's more like pad it more. Remember the last time we stopped somewhere around here? That was when we added the 120. That is here when we added the 120. This is, so it's not saying add 48 more. So they are just more like pad it more up to 48. So this is it. So this extra part were added just to complete it to a set of 64 consisting of 32 bits per block. So yeah, we'll see more why we did it that way. Then the next step says change the 0 indices at the end of the array using the following algorithm. From W16 to 63. Now this is the formula here, S of 0, and this is in the implementation in the verilog. So I will explain this for you using logisim. S small letter of 0. So it's more like a way of obfuscating it in the more probably like hash it. So we are going to repeat these steps for, let me remove this. We are going to repeat these steps for it says for I from 16 to 63. So what he's saying is 16 to 63 is this. When you count this block here, 1, 1, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you're starting from here. Down to 63. So you're going to repeat these steps for W16 down to 63. S of 0. So this is the formula here. For this formula we are seeing here, S of 0, W1, Wi of 15, right rotate. So you can just see simply here. This is the simplification in Verilog. So someone would ask, why are we doing all this? This is the SHA-256 algorithm, how you do the SHA-256 encryption. So this is the simplified algorithm here. So what it's trying to do actually is trying to rotate the bits for each block. That is from block 16 to block 63, and you know each block consists of 32 bits. So that's what is essentially trying to do here. So this is it in LogicSim, how I've implemented it in LogicSim. So this is the input block. I'm going to have this circuit here available for whoever needs it. If I let me show you what I'm trying to think of. So once I'm changing the inputs, I hope you can see what is happening to this output here. So let me change this back to 0. So more like the hashing algorithms. Can you see? I hope you are looking at this output and see for every change in the inputs, you see the corresponding change in the output. So these are more like obfuscation. So now it says x of 6 of 0 concatenated with x of +1 of 7. So what this actually did is it takes 6 to 0, bit 6 down to 0, and changes it to be the MSB, and now takes +1 down to 7 as the LSB. So +1 down to 7 went back, while 6 down to 0 went up. So it's more like rotation, is rotating it. So that's what he's saying here, rotate 7 times. So it's taking 6 down to 0 is 7 bits. Take the last 7 bits and take them to the front, and take the rest down, then XOR it with this. Take the, you see this one says right rotate 18. So now this 17 down to 0 is 18 bits. So it's saying take the last 18 bits and take it up as a MSB, and now take that one down to 18 as the last. Now I said right shift 3. That's what you did here. Right shift it by 3. So hopefully, if you don't understand this Velo code, I still did it here in LogicSim. So this is the right shift here. Right shifted by 3. Now this is where I actually did that implementation of right rotate and left rotate. So you can see here the initial input is 0 down to 32, but these new outputs I mix them up. This is a wire splitter for people who have good understanding of LogicSim. I'm using a wire splitter to do this rotation. So you can see that this set of bits, this signal that went into here, you can see where it came from. It comes from 0 to 17. That's what went to this place. It now went here 18 down to 32. So, and that is the same procedure here also. So I use wire splitter to do the rotation stuff. So please kindly keep together all this Verilog code, because we are going to sum all of them up and get our SHA-256 block. Now the next step says S1. I have to get S1. So S1 is simply, this is what it says. Just like we did in the first tutorial, it says take B16 down to 0 and take them as the MSB, bring them up, then take that one down to 7 as the LSB. The same thing here, take 18 down to 0 as the MSB, and then take that one down to 19 as the LSB, then right shift 10 places. That is S of 1. Let's see what S of 1 looks like. So this is almost the same procedure. Let me show you again. Let's watch this output and see. As I'm changing the input, you see the output is changing likewise. So that's what this does. So now we have this W machine. So I think I'll stop this tutorial here. In the next tutorial, it's already 26 minutes. So continue in the next tutorial. Thank you.